All right, this PowerPoint is going to be on reflection and refraction. All right, so as we look at things that reflect, a mirror obviously is what we think of when we think of reflection, but really everything around you is reflecting light. It's just a mirror does a special kind of reflection where it reflects it and keeps the exact same angle. So it comes in and it bounces off. The angle of incident is what the incoming light is called, and the angle of reflection will be the same. And so in a mirror, you can see an image. When you look at other things, the paper, the book, the wall, whatever, that light bounces in, but then it scatters in all different directions, all right? And that's called diffuse reflection, where it's diffused out. It's not all bouncing in one line exactly toward your eye. It's just kind of bouncing everywhere. So, when we look at diffuse surfaces, it's not a mirror. You're not going to see yourself in the mirror, but let's look at why that happens. When we take individual light rays, and so you have Lincoln here looking at a spot on a wood plank, right? We're going to look at where the light's coming from and where it bounces. And remember, you only see the light that bounces into your eye. It's that final ray that goes into your eye that we see. So light's going to be, from a lamp or from the sun is going to hit his face, and at each point on his face, it's going to bounce in all different directions, and the only light we're concerned with is what bounces and goes into his eye. So as we look at the light coming from the surface, again, the arrow that goes into the eye is the arrow you see. Light is bouncing in all different ways. So if you look at the purple ray here, there's light that's coming from the tip of his nose, and it's bouncing here, and it's going up here. There's light, and there'll be light from the tip of his nose that bounces here and goes into his eye, but there's also light from his hair that bounces here and goes into his eyes. So he's not going to see an image of his nose or his hair. It's all blended together. It's a diffuse. It just bounces all over the place. What he ends up seeing then is the wood, not an image of himself. Okay, we can restrict all this diffused light, and we can restrict it down so that we can only see an image. This is kind of how our eyes work, but this is going to be called a pinhole camera. It's very similar. You have, again, light going in all different directions. All right, so light from the candle is going in all different directions. It's actually going 360 degrees everywhere. And what we can do is we can create what's called a pinhole camera. It's a box with a pinhole, okay? It's really, really simple. And what that does is it only allows the rays that are going through that pinhole to enter. So from the tip of the candle, there is light coming here, but it's hitting the box and, being absorbed or reflected away. The only light we care about is the light that makes it through the pinhole. And you will notice you get an upside down image because that angle will bring the candle image down to the bottom. So a pinhole camera, just like your eyes, the image ends up upside down. Remember, your brain flips the image right side up. But on the back of your retina there, it's actually upside down. And then the light from the bottom part of the candle will actually come in at a higher angle here and end up here. Okay, so a pinhole camera will flip that image upside down, and you get an image at all because you have a small pinhole that restricts the light. Okay, my favorite pinhole camera is actually a deciduous tree. If you go out to any deciduous tree, what do I mean? They got pretty leaves. They're not a conifer, okay? Just a regular deciduous tree. And you look under that tree, you will see circles of light in the shadow kind of dancing around, especially at about noon. Those circles are actually images of the sun. It's not because it's a circle pinhole, it's because the sun is a circle. And what's really cool is if you go out on an eclipse and you look, you can actually see the eclipse in the shadow of the tree in these little circles dancing around. So next time you're on a tree and you see all these little circles dancing under it in the shadow, That is the pinhole camera effect. Okay, a camera obscura, literally this is the same idea. And the first detailed writings was Leonardo da Vinci came up with this thing. But basically, here we go. We have, this is the camera here. Think same thing as a pinhole camera. Here's the little coin size opening. Here is the image upside down. Here's the top of this building. See this ball here? The light coming down, you end up down below. The light from the middle of the building that still makes it in is going to go through that little opening and end up there. So basic same idea as a pinhole camera, just, you know, bigger. All right, as we look at different materials, they can be transparent to light. Depending on the angle, they can reflect. We all have seen glass reflect and glare in our eyes, or water reflect off the surface of the water, the image, or you can also see through it. That is dependent on the angle of light. Okay, how does a one-way mirror work? One-way mirror is just a slightly darkened mirror. Instead of piece of glass. Instead of being completely shadowed on the back, whatever the silver coating they put in, they do it like halfway. And you can actually see through a one-way mirror both directions. What it depends on is which room has the lights on and which room has the darkness. So the way it works is if you are in the bright room over here, you have some amount of light hitting this glass, and it will reflect back, right? It's 50%, 50% of it's going to reflect back approximately, and 50% will go through to the people sitting over here in the dark room, and they'll be able to see you. If this room is dark, there isn't any light going through, hopefully. There isn't any light going through here, and the person over here will not be able to see you. You know, this is where the bad guy stands, and this is where the people who are trying to identify the lineup stand. So this room needs to stay dark for that to work. If you turn on the light over here and you turn it off over here, it's not magic. It'll reverse, and they'll be able to see who's in the bright room, and, you know, that would be bad. All right. Law of reflection, pretty simple. This is just like bouncing a ball. You ever bounce a ball straight up, it comes straight down, comes straight back up. You put it at an angle, it bounces back the same angle, all right? So here's your ball and or light ray, same idea. We have the incident light ray. Incident means think incoming light ray. Boom, comes in, hits the mirror. How do you know this is a mirror? First of all, when we do optics, you need to know this is a mirror. See these little cross hatches here, these little lines coming off of it? That tells you this is a mirror, and it tells you this back side is the dark side of the mirror, the side, the non-shiny side back here. All right, so that's how you identify this as mirror. Plus it says the word mirror, which helps. But if it doesn't, you'll be able to see this is a mirror, not a lens, because it has these lines on it. And we're going to do worksheets that have mirrors and lenses mixed in. So just remember that. So incoming light ray hits the mirror, just like a ball would, bounces off at the same angle. All right, now what angle is that? It is the angle of incidence. We measure this to an imaginary line, the normal, which is perpendicular to the mirror. And you think, why on earth would we measure it to an imaginary line when we have a perfectly good angle we could measure right here? The reason we choose a normal, this imaginary line, is we are going to measure these light rays and reflection on different surfaces. So yeah, this works well here on a flat mirror, but we're going to do concave mirrors, which look like this, like a little cup. We're going to do convex mirrors, which look like this. We're going to do water. We're going to do glass. And so for all those different surfaces, we use this normal, and it's just a perpendicular line to the point of contact here, where the incident ray hits the mirror and the reflected ray comes off. These two angles are always going to be the same. Angle of incidence is always going to equal the angle of reflection. So that's how you can tell where it's going to bounce to. Okay, we're going to get to do this. We have light sources. We actually have this. So this is just like a pre-demo of what you're actually going to get to do. But you can take a mirror right? And you have, here's your angle, here's your incoming ray, and here's your reflected ray. And you know the normal must be right here, right down the middle, because the angle of incidence has to equal the angle of reflection. Okay, ray tracing. So we have, again, you can tell there is a mirror. You can tell that because there's cross-hatching here. We have the incoming ray here hit. And we have the reflected ray here. All right, so incoming ray, reflected ray. This continuation, this B prime is what they call that. This B prime is where this would go if it didn't hit the mirror. We're not going to use that very often, but you just need to know that. So we're going to have incoming, incident. Here we have a wider incoming and then your reflected ray. The normal here would just be straight up and down, and the same thing here. Okay, demo. Who do you see? Or I should say, who sees F in the mirror? This goes along with, if you ever look at the back of it like a semi, a really big truck, they'll have a little plaque on it that says something to the effect of, if I can't see you if you can't see me in the mirror, I can't see you. And the reason is if you sneak up on the right side while they're trying to take a wide right turn and they can't see you in their mirror, if you can't see them in the mirror, they can't see you. All right, so here we go. F. Who sees F? It's a good question. Well, we're looking at light that would be coming in at this angle to the mirror, right? So we think about light that's this angle. We have a normal. We know the normal would be up and down. So now it's just a little bit of plane geometry. Where does that light go? It goes over here, right? Same angle in, same angle out. So dude B would see F. D sees himself. E sees C, and G would see A. All right, so again, here's the mirror. Remember, now this time it just says C. It doesn't even say mirror. This is the back side of the mirror. There is nothing truly back here. Contrary to what my parakeet used to think, there is nothing real behind here. Everything back here with these little primes, this is fake. This is called virtual. It's not really there. All the light is on this side of the mirror. So you have A hits the mirror, reflected ray to B. If you are person B looking at this, what you would see is A. What A would see would be B. Person B, if you were a person, would see A, but where do they see him? They don't see him over here. They see, because here's the thing, your eyes think light goes in a straight line, no matter what. Your brain just says light goes in a straight line. It doesn't account for any bending at any point in time. If once the light enters your eyeball, your brain says that light went straight. Well, where is straight? Straight is behind the mirror. So you see an image behind the mirror. It's not really there. Again, babies, parakeets, and dogs think it's really there. It's not really there, but your brain will see it there because it can't account for this bending, this reflection. That's not the way our brain works. All right, so flat mirror, here we are. Got Lincoln looking at a flat mirror. We're going to start tracing some rays. So off his hair, back to his hair. He doesn't see that one. Off his hair into his eyeballs. That one he gets to see. From his nose, somewhere else, he doesn't see that one. Nose to eyeballs, he sees that one. Okay? Chin into eyeballs, he sees that one. So now we can kind of think backwards into the mirror, into that virtual world behind the mirror. What's that going to look like? He's going to see his hair. Remember, his eyes don't take into account that light has bent, ever. So his hair will be behind the mirror up there, his nose there, and his chin there, and behind the mirror equally so, and that's the image he will see. Makes sense? You've all seen yourself in a flat mirror. Okay, half-size mirror. Do you think he can see his full face? Well, go back to the geometry we just did, or imagine yourself using a pocket mirror or, your makeup mirror, and you know that, yes, that works. Sorry, I went too fast on that one. All right, non-flat mirrors. These are funhouse mirrors, curved mirrors. This one's convex, right? So the way to remember convex versus concave is think cave, like a concave one is like a cave. This one's convex. Things are going to be smaller. Okay, so convex mirrors here. All of these are convex. And what's this say when you have that right-hand mirror? I think it says images are closer than they appear. Well, they're closer than they appear because that mirror makes them smaller. And again, your brain doesn't account for that. It sees something smaller and assumes it's farther away. In the case of driving, that can be dangerous because you think the guy's way back there and then you cut him off, and you know how that goes. Okay, so all convex mirror image is going to be smaller and closer than they appear. Again, we can use, and we actually will do this, convex mirrors and trace the rays, and you will see that the rays all go out. So, and if you were, what your brain has to do to make an image here is it has to follow these rays, these reflected rays back behind the mirror, and you can see they all kind of converge back here somewhere, which is why the image is always smaller. These rays tend to come to this focal point, we call it back here, and it makes a smaller image. So what does he see? All right, remember we're doing this from the normal. So we reflect, and here's the normal. The normal is at a slight angle. So here's your normal. It's not this way, it's up a little. And that causes the light to bend slightly up a little, right? Or down a little here. So this normal isn't what it would be on a flat surface. Okay, same with that normal. It's facing out, so that one's bending down. And your eye traces this back, and you see yourself, again, a virtual image. That means virtual is fake. It's not really there. You can't touch it behind the mirror. Okay, concave mirrors. And for here, I want you to think cave. And these can do two different kinds of images. They can do, you can see the woman's hand. It's larger and right side up. These are the magnifying mirrors you use to do your makeup well. And you know on those, if you back away, the image suddenly flips to smaller and upside down. So these can actually do two kinds of images depending on how close you are to them. On a concave mirror, here's a concave mirror, you can see all the rays come to one point, and that point is called the focal point, okay? They focus on that one point. This is, you will never do this in my class, but you know, if you wanted to take something and fry a piece of paper with the curved mirror, that's where you would put, like, say, a leaf to fry it. And I have one, but it's not quite big enough to do that. All right, so what does ray tracing look like for a concave mirror? So when you are close to the mirror, here you go, you're gonna see a large, this is your makeup mirror, right? Larger image. When you're far away, this is called outside the focal point, and we'll get to that in a bit. Outside the focal point, you're going to end up with a smaller upside down image. And what's interesting about this image is it's a real image. It's really there. And what we call a real image is the one that you can, you know, put on a screen. You can put it on a sheet of paper or a leaf and, you know, catch it on fire. Okay, so these two images are the same thing. This candle is outside of the focal point. It is inside of the center point, but we don't care about that. It all depends on the focal point when we talk about mirrors. So here's the focal point, and focal point will usually be given to you. It's like half the center or something pi. You're not going to worry about it. This center is actually the center of this circle. If you were to create like a complete circle where that mirror is, that would literally be the center point. You'll notice the center is not the focal point. Focal point is closer. So both of these, the candle is behind the focal point. So we're going to create a real image that's upside down and smaller. And there's rules about this, which we will go over because you'll have to do these on worksheets. But basically, if you come parallel in, you go through the focal point. If you go through the focal point, you go parallel out. All right, so there's rules that we will go over. And this one that hits the center line is just the angle of incidence. Here's the angle of reflection. So same there. And you just follow these rays and you'll know where they cross, you get an image, okay? And the image goes from the center line down to wherever they cross, all right? So this image is smaller. This image is going to be larger. It's farther away. Still real, still upside down. All right. Let's look at how you would do, so this is a concave mirror, and for this one, unlike the other one, it's inside the focal point. So this is like when you're doing makeup and you're looking at yourself in the mirror, all right? And what you're going to see is these same sort of center ones and focal point, which again, we'll go over these. You end up with the rays bouncing in a divergent pattern. So if you follow the actual ray from the object, we're just going to follow one real quick. We're going to follow the one that goes parallel in, focal point out. Oh, we'll follow two. How's that? It's parallel in, focal point out. That one we just did. And then focal point in, and the focal point's behind it. So you just use a ruler to kind of figure out where it's going to go. It's still aiming towards the mirror. So when we say focal point in, it's going to go up. Parallel out, it's going to go that way. You can see these rays never cross, right? They're never going to cross. Where do they cross? In an imaginary virtual world behind the mirror. So again, your brain doesn't know that all this has happened. Your brain just follows the rays back and says, well, the image must be behind the mirror. Again, nothing real behind a mirror ever. This is all fake. That image is virtual, but it's larger and very handy to do your makeup. Okay. Reflecting telescopes, these are usually concave. And when we say mirror, loosely speaking, it can be, taking in gamma rays or light rays or different rays. It's still concave for whatever that electromagnetic spectrum ray it is that it's supposed to be sensing. Okay. Refraction. Refraction is when light actually goes through another substance. So we're going to look a lot at glass, but water as well. It's when light passes from air into another substance that is transparent, right? Something see-through. Light's going to bend. And again, your brain never, ever, ever takes that into consideration. Your brain goes, aha, light traveled in a straight line because I know light always travels in a straight line. Well, not true. So if you're trying to go fishing, here's the actual fish where you're going to aim and you're going to be wrong because the real fish is up here, right? The light from this fish comes from the sun. Here's the sun up here. Light enters the water, hits the fish and goes in all directions. The only light we're concerned with is the light that enters your eyeball. That light would take a path that comes up here and bends and then enters your eye. And your eye follows it straight back and thinks the fish is there. Same thing with the pencil you put in. It's not really broken, right? It's not really broken. We can figure out there it is. It's really straight. But your brain doesn't know that. Okay. So there's laws that dictate the angle of refraction, just like there's laws that dictate the angle of reflection. You have the angle of incident and you have a normal. Same thing, just like reflection, all right? But this time, here's your normal. and here's your water, and this is why we don't use the surface. Look at how horrible it would try to be to measure that. That's why we use a normal. Here is the normal, and the angle of incidence comes in, but this time it's not going to reflect up. It's actually going to go into the water, and it's going to bend toward the water. It's going to slow down, and when it slows down, it actually bends towards the water. How much depends on what this substance is. In this case, I just said it was water, all right? But it depends. It can be glass, it can be rubbing alcohol. They'll all have different angles of refraction. But there you go. Okay, so it depends on the medium what the index of refraction is, which means it depends on the medium how much light is going to bend. And you can figure that out. Well, we'll figure it out by measuring it. But there is a formula for it that says the index of refraction, which is n, is proportional to the speed of light. And we take the speed of light to be the speed of light in a vacuum, okay? Over the velocity in that material. So in a vacuum, it would be C over C, which is, 1. But in air, which is slightly, denser than a vacuum, but not a lot. Take a look at it. It's 1.0003. That means that light will bend slightly as it travels from a vacuum into air. Water is 1.33. And then you get some interesting ones, like plexiglass is 1.5, but then take a look at diamond. Diamond is 2.42. And the reason diamonds, when they're, just clear, just like glass, the reason they look so cool and the way they kind of grab light and they talk about light, blah, 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 is that they can internally reflect quite a lot of light because of that high index of refraction. All right, so there is a law that dictates this. It is called Snell's law. It's actually on the next slide, but that's okay. We'll go over it. The index that says that light changes direction when crossing a boundary from one medium to another, and the angle of the outgoing ray makes with the normal is called the angle of refraction, right? So we've said all that. How much it bends is going to be Snell's law, and it's actually, I think, going to be easier when I get to the one on the other page. It's just proportional. What it says is the whatever this material is, air, is this ray and this angle is going to be proportional to this material and this angle. So how much it bends. You see that it doesn't go straight. How far in it bends is going to be proportional to what that material is. When it is entering a more dense material, here's a rule for you. When it enters a more dense material, like air to water, it's going to bend toward the normal. And when it enters a less dense material, instead of going straight here, it's going to bend away from the normal, okay? All right, here's a nice formula. It's actually easier for me to think in formula terms. So here we go. These are proportional. So if this is air, it would be N of air. And the sine of theta of air is equal to N of, say, water, sine of theta of water. Those two are going to be equal. So as we come in and we hit how much this bends, you're going to use this formula. So it comes in and we can do this. How much it bends is going to be that formula. It's going to bend to the N of, say, glass, sine of theta of glass, okay? And then when it goes back out, it's going to bend away from the normal back into the air, and it's going to end up being parallel. So check out what happens in glass, because glass doesn't really distort things. A pane of window doesn't distort, but it actually shifts it ever so slightly. So if you're looking at a ray from an object, here's the ray from the object. Here we go. We enter the glass, we bend toward the normal, we leave the glass, we bend away from the normal. If this is your eyeball up here, and remember, your eye doesn't know that it did this bending through glass, blah, 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 doesn't know that, doesn't take that into account. It follows it and says the image is right here. So normally, this doesn't matter. The glass is thin, you don't really see the shift, But occasionally, like if you go to the Monterey Bay Aquarium, they have some really thick glass. I think one of them's more than a foot thick. And you can actually see that there is a shift when you look at the fish way off to the right. And I'm thinking of that open ocean exhibit there. You can actually see that it's a thick piece of glass, that there's a shift there, which is kind of cool. So you just get an ever so slight shift. Most glass, you never notice it. All right, so here we go, angle of reflection, angle of incident, angle of reflection, and then angle of incident again. All right, which path does light take after entering the wedge? Well, let's think about that for a second. We have light coming in. Here's our normal. It's going into a more dense material. If it were to go straight, it would be A. If it did some kind of crazy bounce, like a mirror here, it would be C. It's not going to be either of those, right? It's going to come in and bend toward the normal. Okay, now look at it exiting. Which one do you think it is when it exited? If it bent toward the normal when it entered a more dense material like glass, what happens when it leaves that material and enters air? All right, lenses. Concave lenses shrink the image, and convex lenses magnify the image. Lenses and mirrors basically do the opposite thing. So when you think of a concave mirror, it'll act like a convex lens. And a convex mirror will act like a concave lens. All right, so let's look at what's going on. You have a concave lens. You're going to end up with a virtual image behind it. Why a virtual image and why behind it and why smaller? Again, your eye is going to be over here somewhere. It's going to take these rays of lights that are all going in different directions. They're not ever crossing on this side. And it'll say, aha, they must have come in a straight line from behind here. And it'll put the image back there somewhere. And that'll be a virtual small image. Okay. This is your classic magnifying glass, and this is a real image. Yes, you can fry leaves with this at the focal point. Okay, you get a real image. It's upside down on a convex lens. Yeah. Okay, total internal reflection. At some point, as you do this, at some point, the light will actually come back into the water. So when you take light and you're shining it out of water, and yeah, I know that flashlight, like it would fry and the batteries would fry because that doesn't look like a water safe flashlight to me, but whatever. We have light from a flashlight in the water and the light's leaving the water. Cool. And they keep changing the angle and the light leaves the water. At some point, that light will bounce back down into the water, and it's usually when it's about 90 degrees here, which is 45 off the normal. Okay, that's the critical angle. And so you can see that light will sometimes water will sometimes act like a mirror. All right, and that just depends on the angle. So you can do that with glass. You can see in this case the glass reflected the laser instead of refracting it. So what we normally would think of is this light would come in here and it would leave at some changed angle. Well, it actually reflected it like it was a mirror. This is not a mirror. This is a piece of glass, and it reflects it again. Why? Because these are 45-degree angles here. So you can look up and you can see the sky. Okay, but if you look over, what you see is the light that has reflected from other areas of the ocean or, swimming pool or whatever. Okay, so here you get to see it. They actually put a little disc there so you can measure it. You have the light coming, and when you hit this 45, oh, here, let me start up here. You have the light going, and it goes out. Dark room, here it goes out, right? You can actually see a little bit is reflected back in. And as you move that light angle up and up and up, more of it's reflected in. And then you hit the critical angle, this 45 here, where it's going to come at a 90. Your normal would be right there. Now all of it is reflected into the water. All right, that's how fiber optics work. is that you just never get past that critical angle. So you can keep light inside of something by never getting past that critical angle. Also, the fun toys at Disneyland, they work the same way. There is one of those camera obscuras at the Cliff House in San Francisco. I've been in that one. It's kind of cool. You can see the ocean, and they project it on a large center area, actually. So that is kind of fun.